all the background that comes sort of like before all these things that we as engineers are interested in, like biodiagnostics, biomeasurements, and biomonitoring. A little bit about my background. I have so far, I was introduced to Aquaphotomics in 2011, so it's quite a number of years. And I had experience in working on all these sort of like research fields with really different aqueous and biological systems. The only field that I really did not touch yet using Aquaphotomics is microbiology. Maybe I'll have it. I hear it's pretty interesting. So all this research experience allowed me to sort of like gain insight and to see some repeating patterns, because in all these systems the water is a common element. And I was exploring this water as a common element using various types of spectroscopy: ultraviolet, mainly visible near infrared, and infrared. And with all these different types of spectroscopy, I used I was applying the same tools, the tools that I learned from Professor Tsenkova in the COPE laboratory, NIPS laboratory. So these tools can be summarized as multivariate analysis, and all these tools have the purpose of extracting these water absorbance bands to see what water is doing in all these systems and processes that I was interested in. And we sort of like tried to publish the methodology of this, of using these tools in this recent paper. So if you're interested to sort of like gain a better insight, please just check out this paper. The point is that why I'm mentioning this is that these same tools are applicable in every type of spectroscopy that you use, and it is very, very important to use these tools to extract the information about water, because this information is really hidden and subtle, so you really need good tools. So what these tools are actually allowing us is to sort of like compile all this information, knowledge about water, and we've been doing this for years. And what you see here presented is just one small part of the really large database of water absorbance bands in, for example, visible, near-infrared, short near-infrared, far infrared range. And we are trying to sort of connect what we observe in the systems that we are working with, what is related, when we observe certain structure, to correlate that structure with the functionality that this structure has, and to use this knowledge for applications in these various sorts of applications that I'm going to mention today. And what is missing now in all these columns is I'm always interested in relating the things that we know about systems, like you heard, for example, from Tanaka sensei or from Christina just before, to really relate some things like water activity to the specific water bands, to the specific water structure, and this is really, really important, at least for me. So based on all these elements that I mentioned, and based on really a lot of work that has been done in this area, to which all of you contributed, because I really read a lot of your papers, and even if we don't know each other from before, believe me, we spent hours together. I was reading lots of your papers. And based on all these things, based on my experience, on the things that I read, and sort of like discussed with all of you, I sort of like saw some patterns in this, repeating patterns in these systems and in our analysis that are shaping my knowledge about water. It is still limited, but I see this sort of like new knowledge emerging. And the main messages that I'm going to try to convey to you today, this stems from this new knowledge, is that first, water acts as a sensor and an amplifier, which is terribly important for the measurements. The second thing is that water is an active biomolecule, and I was actually thinking whether to phrase this as water is an active biomolecule, or to say that different water species have different functionalities. So I will use these terms sort of like interchangeably. And from these two messages comes the third one, and it is that based on what we know about water, is that we can rethink the way we think about the way we approach the measurements. And this brings really a paradigm shift and opens new possibilities for biodiagnostics, biomonitoring, and various sorts of biomeasurements. So current approach to biomeasurements is very restricted, and I think that the current state of the art has sort of like reached a plateau level. In the current approach, water is seen as a passive inert medium in which all sorts of chemical reactions happen. So, for example, in biodiagnostics, we're always interested in certain biomolecules like proteins or lipids or whatever, and we see them as functioning in sort of like in a vacuum. When they're presented in simulations, they're presented on the black background as if the water does not exist, and that's not really a case. So, from this approach comes our approach to the measurement. We are always interested in, for example, in spectroscopy, in absorbance bands that are related to the structure of these biomolecules. We are looking at the, let's say, absorbance bands that are related to protein structure and so on. So the problems with measurements arises when the concentrations of these biomolecules is very, very low. So we don't have actually these absorbance bands. And the current trend, for example, in biomeasurement is to try to amplify the signals that come in from these biomolecules. And one of the really recent trends into which a lot of money has been invested is nanotechnology. And nanotechnology is used to amplify the signal coming from the biomolecules. And to just shortly explain their logic in nanotechnology, the point is, for example, you have a one target protein, and you can catch this target protein using antibodies. So when you use nanoparticles have a really large surface that you can functionalize. You can put, for example, 100 strands of synthetic DNA. So when you put one antibody to these nanoparticles and 100 synthetic DNA strands, this nanoparticle will catch these target proteins. And what you achieved with this approach is that you are actually amplified, and you're not able to measure one molecule, but you amplify the signal of this protein using 100 synthetic DNA strands, so you amplify the signal. So this is an indirect approach. It takes a lot of steps and lots of money to be developed. On the contrary, in the aquaphotomics approach, we do see water as an active component, which actually is directly influenced by all what is happening into it. So it hydrates all these biomolecules. When they change the structure, the water matrix is changed to accompany this structure. So what we are monitoring is also indirect way, and we are looking at water absorbance bands that are always there, and they are always abundant and in high absorbance. We have really always good spectra, so we can monitor these changes. Why we have this strong signal of water? Because in all biological organisms, water is the dominant element, right? And from this knowledge, we actually can use the water as a natural amplifier. We don't have to invent all these sorts of artificial amplification. We have a nature that allowed us to do this. And this is in the heart of a aquaphotomics approach, and it is actually not very new. The point is that this indirect approach to measurements was reported 30 years ago by sort of like a pioneers in near-infrared, which I cite here in this paper. They reported that they were able to measure salts in water. And salts, since they don't absorb in near-infrared, illustrate perfectly that you can measure anything by using and looking at the water absorbance bands. This is further confirmed in a study by Goen et al. And recently, the detection limit was sort of like analyzed to see whether this approach really brought some novelties into near-infrared. And as this review paper actually cites, this approach allows at least a 5 times higher detection limit using this approach. So from this knowledge comes this message. We can use these properties of water as a sensor, as an amplifier. We can see it as an active biomolecule, and we can use all this to approach our measurements. And I'm going to illustrate all these messages on 3 types of systems, applications of aquaphotomics in the problems that we, for example, had with measurements of biological fluids, measurements on plants, and of course in biomedical engineering. with humans. So my first example comes from the cows, from the research on milk. And cows played a very, very significant role in development of aquaphotomics, because the entire aquaphotomics was developed based on the findings that we can measure all these components, proteins, lactose, fat, the standard milk components, based on the water absorbance pattern. And you can there are really lots of literature available on measuring of these standard milk components that we usually want to know. And we are currently in the process of actually compiling all this knowledge into a monograph, so you can actually expect this monograph in the course of next year. Today I'm going to show you just that apart from these components that we already showed that can be measured, we also, for example, try to measure something that is usually not measured using water absorbance bands, and these are fatty acids. Usually when people talk about fatty acids, that's fat, lipids, so we're not looking into water to measure lipids, it's sort of like ridiculous. But we took this approach to be even sort of more ridiculous. We actually used two approaches. We used whole milk, and we centrifuge milk to remove this fat even further to see what's going to happen and to see whether we are able to measure these fatty acids. So in the raw spectrum of milk, what we saw in the whole milk, for example, we saw that, of course, it is dominated by water. Water is the main component of milk. And in our measurements, we also had, of course, the problem of individuality. Each cow is really very, very specific. So we had to build all these models for fatty acids for each cow. Based on the results of PCA analysis for whole milk, we had some further insights. So, for example, we saw that the milk that was collected in the morning and in the evening was really, really different, and these differences come actually from the amount of fat. So this meant that we have to not only build separate models for each cow, that we also had to build it for the milk from the morning and the evening. And, for example, since we collected this milk during some period of 14 weeks, in whole milk we were not able to observe differences between the weeks, so we could not see the influence of time. But in, for example, centrifuged milk, we saw that we don't have this tendency of separation of morning and evening milks, which has consequence that means that we can build one model for one cow. And further, what was very, very interesting is that we had this really nice separation over the weeks. And we were able to see this when we removed this really large, let's say, percentage of fat. We were able to sort of like enhance the influence and the information that comes from water. And this is very, very informative about, for example, the feeding system. This can bring us, for example, information on how to influence the feeding system, the development of disease, or, for example, the therapy of cows, and so on. So this nicely illustrates the approach that if you prepare your samples like milk in a different way, you can actually use these properties of water to extract the features that are of interest to you. However, due to the, of course, practicality, we focused our development of our models for the whole milk, because it is much easier to just collect whole milk, right, than to centrifuge it and then try to extract information in fatty acids profile. So we developed all these regression models, and from 18 fatty acids that we were interested in, we were able to, with very nice accuracy actually, model 11 of these mainly short chain fatty acids and, well, let's say, middle chain fatty acids. We were not able to develop actually models for these few fatty acids, but that was actually due to they were really, really in small concentrations, and we did not have enough variability in these dependent variables to sort of, we were not even able to build the models for this. However, this is really a good step into the step forward, for example, compared to the state of the art, because currently, usually infrared spectroscopy is used on the dried milk, and we have this for whole milk. And we sort of have additional information that came from this research. For example, I told you that if we centrifuge milk, we actually have information about the influence of, for example, feed, or for example, not only nutrition but health status of the animals, so we can monitor that. We can certainly measure many analytes simultaneously, and some of these, some of the things that we were able to predict were not even analytes. We were, for example, quite successful to predict with quite reasonable accuracy the milk yield of the cow. So we were able, based on the milk spectra, to predict how much milk each cow is going to produce each day. So that is one thought for you to, for example, explore that some not only analytes can be measured from the spectra, but something like milk yield, or for example, you can correlate things like wettability of surface with, for example, water spectra and so on. My next thing, so I really hope that this illustrated my first message, that the water acts as a sensor for variety of things, and that it acts as an amplifier. So I'm going to now move to the plants, and I really, really love plants. Why? Because unlike cows, plants do not have that high individuality, so they sort of like are less different one to another. And that allows me insight into this other very, very important aspect of water, and that is that water is definitely an active biomolecule. I don't know why we don't call it biomolecule. So different water species have different functionality. Maybe we can even say that we have different water biomolecules. And this is something I've learned from the plants. So one of our very recent research was into zucchini plants, and the objective of this research was actually not following the growth of the plants. We were interested in measuring something completely unrelated to the growth. But during my analysis, I was sort of like sidetracked because I noticed some very, very interesting phenomena. So what was this phenomenon? We noticed that we have to, in order to measure some compounds in the leaves, that we have to separate, actually to build different regression models for the old leaves that come from actually they're called cotyledons, and we have to separate and build models for the fresh, newly grown leaves, and these old leaves that are sort of like drying and dying during this period that we measure the plants, and we follow these plants for several weeks. So I wanted to know why these leaves that are dying are different compared to these fresh, newly grown leaves, and I did, of course, the PCA analysis first to explore this issue. And what I saw, of course, so we had these cotyledons that you see they're yellowing and they're dying. They're really markedly different compared to these old, newly grown, lovely, fresh green leaves. And these cotyledons were in the left part, in the negative part of this PCA and space, and these were on the positive line. So when I explored this loading vector of the PC1 component, I noticed the three characteristic absorbance bands. So in the negative part, where I said there were cotyledons, we had this band at 1391 and 52 nanometers. And in the positive part, you remember there were these fresh leaves, and I noticed this band to 1441. So these two bands were related to the, let's say, functionality of water in cotyledons, in these older leaves, and they correspond to trapped and bound water. And I saw that this is actually reported elsewhere as a property of drying process in food, for example. So I knew that this is a property of drying process to see these two waters. And I saw this again, I saw the dimers are important for these growing leaves, and I saw that somewhere else. I was really, really fascinated that I saw this as a property of really nice living creatures, and I remembered our previous research. Our previous research was concerned with establishing what is the difference in water in the leaves of the plants that can survive long periods without water, and the plants that cannot do that. So we investigated these plants are called resurrection plants, like Jesus. They can resurrect, so they sort of die without water. They look completely dry, and then you give them water, and within hours they're all fresh and living and happy and so on. So what we noticed, for example, just by monitoring water content, we saw that this plant, which is a relative of our Jesus Christ plant, so this plant actually is trying during dehydration to keep this water as much as possible, so sort of like trying to retain this higher percentage of water, while this other plant, our plant that we were interested in, was readily losing it. It was like, okay, I don't need this water. Just, you know, I'll continue to live, obviously. So what we when we did some multivariate analysis, we saw that for this in the spectrum of these plants, in the leaves of these plants, a certain water species are important. And Professor Tenko then came to this fantastic idea. Let's see how the ratio of these important water species behave. And what we saw that in this dehydration process in our friend Haberleia, this lovely resurrection plants, the ratio of these water species, of protonated water, free water, and these water molecules with various number of hydrogen bonds, are kept constant. So she's losing the water, but keeps all these ratios constant, which means that she just basically shrinks in size without the major damages to its components. On the other hand, the other plant, its relative, has fluctuations. So she's trying to keep water, but actually is fighting to prevent the damage, which actually ends up quite poorly, because these plants cannot survive if she has less than 35% of water. In our resurrection plant, what we saw, in this completely dried state, which sort of like corresponds to, she's totally dried, but she's still living, we saw one thing that is really, really fascinating, accumulation, really, really large accumulation of water diamonds at the expense of free water molecules. The previous speaker actually sort of like talked about a little bit about this activity of water and so on. So these free water molecules are very, very important for water activity. And we have in this other plant a high percentage of this free water, which is actually really needed for all enzymatic processing and so on. So the high percentage of free water is the cause of the damage of this plant. On the other hand, we have a completely different picture here. And I was also interested in why this happens. Why do we have this dimers? Well, the first thing is that in this final phase of dehydration, this plant accumulates sugars, very, very important sugars. Tanaka-san mentioned that sugars are very important, and in this case, this is special sugars, sucrose and raffinose. And these two sugars are working actually to establish a glassy state of water, which is sort of like characterized by the presence high accumulation of these dimers. We do not know exactly what is the cause that these dimers are important. I only found, for example, from the atmospheric chemistry that the water dimers are very, very important in certain reactions of oxidations, and that they actually provide 3.5, let's say, much faster reactivity time in certain chemical reactions compared to monomers. And this may be the reason for very, very fast recovery during rehydration process in these plants. And this process of recovery is actually, within hours. And what I wanted to point out with mentioning this sugar is that the resultant water structure comes from genetics. So it starts with genetical information to these various sort of, let's say, metabolites and proteins who function together to create this type of water structure that has this type of functionality. And one more thing that is actually showing that this information, that the water structure is actually governed by or sort of regulated from genetic information. We examined cold stress in soybean plants, which were genetically modified to have different levels of cold stress tolerance. So we examined actually 5 types of soybean plants, ranging in this tolerance to cold stress. And what we noticed is that the cold tolerant plants, this is only an example for comparison with the plants with highest tolerance and the plant with lowest tolerance. We saw that these plants that have high tolerance to cold actually always keeps this water structure in a sort of like a bulk state and in less hydrogen bonded forms, which means that it is much, much harder to sort of create ice crystals when you have this disconnecting water, less hydrogen bonded water. And where is this water structure coming from? Why do we have so much, let's say, free water still, this less hydrogen water? It is related to the action of aquaporins. And aquaporins can sort of be, of course, are regulated based on the genetic information. So from the plants, we learned that we can sort of like manipulate this water structure and achieve different functionality in plants. So this is very, very important that we can manipulate that, and not only in plants, because this is applicable, of course, to all kinds of biological organisms. And this leads me to the end part of my talk, which was concerned with monitoring, biomonitoring, and on the example of, for example, monitoring of spent dialysate. I would also like to point out some novel things which Aquaphotomics offers. So what is dialysis? It is a kind of therapy just invented for the patients who does not have functioning kidneys anymore. And this is just the process of blood filtration. This process is currently not efficient and not monitored because we don't have good enough methods. So why do we not have? Because, as I mentioned, with the current approach to measurements, we are focused on measuring these various biomolecules, concretely with this dialysis, usually on monitoring urea and creatinine. But there are like 80 various types of uremic toxins that actually contribute to this uremic syndrome in patients. So it is absolutely not enough to monitor just 2 or even 10 of these. So our approach is actually to monitor the cumulative effect of all these changes in all these uremic toxins and other components in the blood by using their effect on the water structure. So again, indirect approach. And what we did was we collected this spent dialysate during this analysis. So this is sort of like a biological fluid which extracts all these toxins from the blood. And we collected this dialysis in 4 different time points of the dialysis in like 20 of patients during I think 17 therapy sessions, something like that. I can't remember now. So with this monitoring of spent dialysate, I did some analysis in UV region because there are some reports that the UV region was actually used for monitoring. Some of these uremic toxins actually absorbed in UV region, so it was quite, for me, interesting to try. And it was very interesting to see that in UV, as you see, as the dialysis progresses actually, the spectra of this spent dialysis is actually approaching the spectra of pure water. So I could actually just measure the area under the curve of this spectra and to sort of see that my dialysis, that my spent dialysis is becoming more and more pure. And it is very, very interesting that I actually find that there is one research group who was really focused on using UV, but they did not at all use, for example, or compare this spectra to pure water or pure dialysate. But they did ask a question: do we only see these analytes in this dialysis? However, because UV is sort of like destructive and so on, it can be dangerous. Of course, I was more interested in using near-infrared. And this agrogram is actually showing us the state of water in spent dialysate as the dialysis progresses. And as I said, instead of monitoring all these like 80 components, what I saw in spent dialysate is that as the dialysis progresses, the dialysate becomes more and more clean, and I could see that by the increased absorbance in only 2 bands, which are related to actually free water. So this opens up a possibility of using actually this type of information as a new biomarker. We don't have to really only use this like urea, creatinine. We can only monitor what's happening to water. And this is really, really useful. So with this, I'm going to end my talk, and to invite you again, I really hope that I was clear with my messages, and I'm sorry that I did not provide experimental details, but all this, all that I talked about today is either in the process of writing or either in the process of publishing, so you will see it, whatever you're interested in, very, very soon, or you can just talk to me. And I would just like to end by acknowledging very, very briefly the financial support of Japanese Society for Promotion of Science, who allowed me to actually perform my research here in Professor Tinkova's lab, and to the following colleagues, Dr. Dimitar Giuliano, Dr. Daniela Mojankova, Dr. Shinichiro Kuroki, Dr. Hiroyuki Morita, and Dr. Stefka Atanasova, who actually performed this study on resurrection plant, and I joined in the sort of like last moment. And to Dr. Hideyuki Inui and Dr. Petya Stoikova, who are working with us on these zucchini plants. And of course, I really need to thank the patients and staff of the nephrology clinic who allowed me to perform the dialysis research. And of course, thank you very, very much for bearing with me today.
Thank you very much for this wonderful review. And we are now open to questions. Take questions from the audience. Okay, Bernard starts and we'll do it. Professor Paul.
So, in support, thank you for your really nice presentation. In support of the first part of your presentation about the fats, the low to medium chain fatty acids on water, we recently looked at ghee, which is basically clarified butter, which contains those short to medium chain fatty acids, but no protein. And we were astonished because we looked at the exclusion zone next to cylinders made of ghee, and we were astonished to find the largest exclusion zones of anything that we've studied in the past.
Fantastic.
So it looks like a real change in water is initiated by those in support of what you found.
Thank you. Really nice to know that.
Okay, next question, Professor.
Jelena, thank you very much. Very inspiring as always. I could not follow where you were describing the ratio of species, the blue and yellow slide. Yes, this one. Where does the data come from? Sorry, I couldn't follow you.
Okay, so the data comes.
Where does the number come from?
Yeah, I understand. So, we first did, for example, principal component analysis, subtractive spectrum, and second derivative spectra, and all this analysis indicated that we had changes in this resurrection plants, in the two plants at water bands, which correspond to this water species. So then, what we did was to of the spectrum, and then to extract these values of absorbance. So at each moment of the dehydration, at each hour of the dehydration, we would sort of like sum up the absorbance of all these species, and then calculate the ratio that the absorbance of particular species has in the whole sort of like sum. So this is how we calculated the ratios.
And you got the ratios like from the amplitude of the loading vector, for example?
No. This comes. The ratios comes from the absorbance.
So
EMS
corrected
absorbance. Yes.
Thank you.
Okay, next question, Professor Hook.
Yeah, thank you very much, Jelena, for this very nice and stimulating talk.
Thank you.
I found a very interesting one of your approaches, but there's not enough time to discuss about everything now. So I just wanted to give you a brief question or remark concerning plant analysis. And I wanted to ask you, have you ever tried to correlate your findings of the water pattern with primary or secondary metabolites?
Mm-hmm. Yes. Well, for this, for example, with this resurrection plant, we had measurements of these sugars. For example, raffinose, sucrose. Then we had glutathione, oxidized glutathione, RAS, antioxidants and sugars and some acids, amino acids. So the point is that we did establish regression models, for example, and we saw that we have very nice correlation with, let's say, certain water species and these sugars. And we also, for example, did the regression on time, then regression on water content, and so on. So we do have this.
And did you also try to correlate it with secondary metabolites like flavonoids or whatever?
Well, we don't have this. For example, this experiment we did not measure that.
We should discuss about this.
Thank you. And last question here, please.
Yeah, thank you, Jelena. I'm also fascinated by this figure here with the resurrection plants. So, do you have any idea of the mechanism that happens here?
The mechanism.
Could it have anything to do with the aquaporins, or what?
In this plant, I'm not sure. I think, I'm sort of like certain that it has to do with sugars, because sugars form this glassy state, sort of like a vitreous state of the water, and this is what preserves all these, for example, membranes and all these biological structures in this intact state. So this is what allows survival in this phase.
Just one comment.
Just an additional comment to this. This is absolutely right for S4, the glassy state. Aquaporin is making free water molecules, and we have seen this. So the free water molecules are drastically decreasing, so you might be right. But we have not analyzed aquaporin, which is particular time, but that might be the mechanism. Yeah.
Okay, thank you for your questions. I'm sure there's a lot more, but I would like to kindly ask you to
Thank you
transfer
very
them
much.
to transfer them.